Hey guys, it's Robbie again with another practice exam breakdown, and very exciting. This is our last practice exam breakdown, and I will say that unfortunately there may be a final practice exam given by Dr. Outlaw. However, since it's a very long practice exam and it's basically all multiple choice, I will unfortunately not be recording a breakdown video of it just because of how long that practice exam is, or potentially will be if they decide to post a practice exam. But this video will be broken into two parts, very similarly to practice exam number 3, where I will be covering the all the announcements and all of the kind of very big picture things that you need to be worried about for this exam, and as well as the free response questions. And then Corey will take over the multiple choice portion of the practice exam. So, again, at this point of the semester and at this point at Charlotte, you've probably taken Gen Chem 1 here. If not, you've already taken three exams here. It's the very same format. Just put your first name, last name, sign your name, remember your student ID number, and check which section you're enrolled. You'll be given a periodic table, the exam information sheet, and an answer sheet. The only portion of the exam that's graded is the answer sheet and the free response questions. And yeah, for the actual exam information sheet, I did not really have much annotations that was pretty significant that helped me on the exam. If you want to kind of circle the important equations that we will use in this exam, starting from here all the way, not this one, that's electrochemistry. All these equations are fair game. And the only reason why I circle some of these, the quadratic formula and what a quadratic graph looks like, is just in case of an ICE table that may involve with that. I sincerely doubt that you're going to have to deal with this. This is more of a exam 3 kind of thing, and in acid-base chemistry, we could really use the rounding rule or the rounding assumption much more commonly than like chapter 13 material, I believe, when we're initially talking about equilibrium. But yeah, I also want to talk about this equation right here. This is pretty relevant in the question 20 part C, and we'll break this down a little bit more, but I just want to talk about how this equation right here is just a rearrangement of values to get this equation that we used pretty commonly. All you need to do is just divide by negative RT to get negative G naught over RT, and it will result in an equation where it's negative G naught over RT equals the natural log of K. And as we discussed with any logarithmic algebra, you just need to raise the power of the base. In this case, for a natural log, the base will be e. So raise everything to the e, and that'll cancel out that natural log. So e of negative G naught over RT is going to equal K. If you're not good with this derivation, I definitely recommend just noting this down within your exam information sheet, but I think we've done much more difficult algebra in our time at Gen Chem 2. Overall, I feel like this exam is just mostly conceptual in identifying what kind of delta G equation we're going to be using. I would also just mostly focus on the conceptual portions of this chapter because that's where I believe the most of the difficulties and the kind of confusion lies here. All right. With that said, let's just go over the free response questions. So for question 15, we're given a couple of scenarios and we're going to predict whether the entropy or delta S is going to be less than 0 or more than 0, either negative or positive. So for statement A, we're talking about the deposition of iodine. And if you do not remember what deposition is, that is just going from gas to solid. Let me write that down. So if you do not know what this looks like, if you've seen frost forming on some object that is very hyperfreezed, that is an example of deposition where the water vapor in the water, the water vapor in the air instantaneously goes from gas to solid to form frost on the liquid container or whatever container you have that is very cold. So as we talked about in entropy, gas is going to be a higher disordered thing, so the inherent S value of S is going to be higher. While solids are more ordered or more structured, so the inherent S value of this is going to be lower. Since we're going from a high disordered thing to a low disordered thing, the delta S will be negative because it decreases through this change. Very similarly with statement B, this is just the vice versa of this. We're going from a aqueous solution, which is a little bit more organized and comparatively to gas has a lower S value, while a gaseous form of anything will have a higher S value. So for this one, the entropy is increasing and the change is positive. And then this is just a callback to what a combustion reaction is. Butane is C4H10, if I remember correctly from organic chemistry. And basically with any combustion reaction, a hydrocarbon or a alcohol reacts with oxygen, dioxide, and water is formed. So if a liquid plus a gas going to a gas plus gas, the gas has disorder just because of the matter it is compared to all the gases on the product side. So in terms of entropy, the reactants will be lower and the products will be higher in entropy, meaning that delta S will be positive. Question 16, this is one of our titration curves, and just by this is going to be a weak base as our unknown, just because we're starting at a high pH value, and it also has this little dip in the beginning. Just to break this down, this is the initial point. Right here is the half equivalence point, and if you forgot what this is really relevant for weak acid, weak base type curves. And this is where the pH, the pH will equal the pKa, as well as the and the conjugate will have equal values. And then point C is an equivalence point, that is the most vertical point of any titration curve. This is where the base added and the, that's just the equivalent point here. And then D is just at the end. All right, so knowing this is a weak base, we can already know that any unknown saying it's an acid statements are completely incorrect. Then, just based off of only one equivalence point, we know this is a this isn't a monoprotic base, because that's not a thing that we talked about, but it is a base that can only accept one proton, not multiple protons. So this statement is true. And then just curve, we already said this, that the unknown is a weak base, not a strong base. So this question just really demonstrates how important it is to memory what the titration curves for specific unknowns look like. Just take a look, draw a figure, have something, exam information sheet, kind of reminds you of what it looks like. There are some trends with the titration curve that you can just pretty easily recognize that curve. All right, and then part B, which titration point shows what is equivalence. We already talked about this. This is going to be point C, where the inflection is at the most vertical here. So that was a very ugly C. All right. Question 17, draw the 3D structures of carbonic acid in part A and its conjugate base. And for part B, this is going to be include its structures and dashes and wedges when needed. So I just the key, because this is a little deceptively difficult to draw. So as we talked about with any Lewis structure or any structures that we talked about, the central is going to be the one that's the more electronegative. For this case, it's carbon, because just organic ones will have the carbon backbone. So this carbon right here is not tetrahedral, this is trigonal planar. So we don't have to worry about any wedges or dashes, just because of the double bond between here and O, and two will be in the same plane just based off of what trigonal planar is. Then these two oxygens here are tetrahedral, and the reason why we can get away with having this hydrogen in the same is that the tetrahedral generic structure has a center atom labeled as X. It will have two groups in the same plane, which would be the hydrogen in this case, and it will have two groups that will be a wedge and a dash respectively. So if we can say that the two electrons here are the wedges and the dashes, we don't have wedges and dashes, which makes the drawing of carbonic acid actually. Then whenever we're making a conjugate base, all that is carbonic acid is just going to act as, so the hydrogen bond either here or here, doesn't matter which you pick, and the lone pair will go to the oxygen, making the formal charge negative. And since can kind of pick oxygen have the double bond in which oxygen can be a formal charge of -1, there will be resonance between these two oxygen groups. Alrighty. Question 18 is talking about a solution of nitric acid with 2.5 molar and its conjugate of 0.3 molars. And we're given the Ka of the of nitric acid, and we're to figure out each of the solution, which just based off what we're given in the equation, immediately you should go look at the Henderson-Hasselbalch equation, which is pH equals the negative pKa plus the log of the conjugate over the acid. So just values that were given right here are given in the form that we need it in. We'll get negative log of 4 times 10 to the -4, which is our pKa, log of our conjugate over the acid. When you're doing the actual calculation, I want to remind you of the sig fig rules of logarithms. basically, whatever is within the logarithm, this will be 2 sig figs. So the logarithm will be 2 places after the decimal point. So if you had 3 sig figs here, you'll go 3 decimal points after. We do not care about the ones place. We only care about the decimal points for saying which number is the least or the last significant digit. Very similarly, if you take the log of here, both of these numbers are 2 sig figs, so the number that you get from here will be rounded to the hundredths place, or 2 places after the decimal point. Adding these two together will give you a pH of, let me do it real quick. A pH of 3.42. And this is accounting for the addition subtraction sig fig rule, where we're just looking at the last place significance. Since both of these are in the hundredths place, it'll just place. All right. Question 19. This is basically what I would do. You're given a that contains 0.25 molar of our acid and 0.42 molar of our conjugate base, and A of our acid, and we're asked to calculate the pH of the buffer after 1 gram of sodium hydroxide has been added. So this will be a weak acid strong base titration, where if you draw out the actual, it will go to full completion because this is strong. So the fire table, that's what you'll have to use. We'll have to initially get molar amounts of these values. So for our acid, all you need to do is just convert the 150 ml of our initial buffer solution to liters to cancel out the moles over liters of the concentration. And as a result, you get 0.0375 molars. That will be your initial here. And then very similarly for our conjugate, you just take the volume of the buffer solution times its concentration to get the molar amount. Put that at its initial. And then for NaOH, this is going to be a little bit, to do is first get the molar OH, which is just simply periodic table finds molar weight would be 3.998. Then for every mole of NaOH, you're gonna get OH just because it is a strong electrolyte, so it fully dissociate to our hydroxide, which is important for base chemistry in this. Yeah, good. 0.2 moles of hydroxide. Earlier, hydroxide is a very strong base, so it will react to full combustion. So change it fire table, it will be R. It will be negative 0.025 mole on the reactant side, and then on the product side, it will be positive 0.025 mole. As our equivalent point, we will have 0.125 mole of hydroxide and 0.0880 mole of our conjugate. Now, we're given Ka. We know our concentration in molar amount of our acid and its conjugate. This screams Henderson-Hasselbalch very similarly to what this equation was saying here. And generally, I've noticed that if you're given a Ka value, most likely you're going to be figuring out the pH given the Henderson-Hasselbalch equation. So putting values in, plugging them in, you'll get 201, where 0 is the significance because this is 2, and 0.847, where the significance ends at the thousandths place because sig figs, there's 3 sig figs for this value, so it'll be 3 decimal point, or 3 places after the decimal point. Just back fig round to the last place of significance, and since the last place in this case will be the hundredths, our pH will be rounded to the, so 4.201 plus 0.8476, that will be roughly 5.05. All right, and then very next question, just a plug and chug, and where I say that the with the entropy chapter, or yeah, the entropy chapter, or chapter 14, this is where you just need to look at given to you and find a equation that relates to that. So here we're given action that H naught, and we're asked delta G naught in kilojoules. So the equation that most fits that information is this equation right here. The delta G equals delta H T delta S. So you have to convert your temperature to Kelvin, and it's just 73.15 plus its degrees. And plugging in the actual numerical values in, be very careful. I would say it doesn't matter which number initially that you convert, but you have to make sure that the kilojoules and the joules have the same prefix to each other, because analysis and unit conversion, you cannot subtract joules to kilojoules. It doesn't work fully, so you either have to convert this to kilojoules or this to joules. Since the question A is asking for kilojoules per mole, I would change the reaction to 0.265 kilojoules per mole Kelvin. So plugging that in, just follow your sig fig rules that we've been doing all year. This will end at the ones place, just based of our sig rounding rules right here. This is the leftmost place, so to 98.15, that has 3 sig figs, and then this has 4 sig figs, so whatever product here will have 3 sig figs. And then following our addition and subtraction rules of sig figs, it will be the leftmost place. This will be, I believe when I did the calculation, it was in the hundredths place where significance ends. This is in the tenths place. Since this is the leftmost place where significance ends, whenever you put that in your calculator, you should round to the tenths place. And then very similarly to question A, at what temperature does this reaction switch between non-spontaneous and spontaneous? It's just language saying, what is the temperature to G equals 0? So again, here for delta G, put in information, leave in the information. This time it does not matter if you put this as joules and this as joules, or both of them as kilojoules, whatever you prefer. But since we already did kilojoules over here, what's consistent with both of the units being kilojoules. So plugging that in, it follows very similar sig fig rules as before, and all you need is just and the way to do this is add T to both sides, and then you'll divide by negative 0.2645 kilojoules per mole Kelvin. Doing you'll get, and as you'll get joules per mole all canceled out, and then 1 over Kelvin will just be Kelvin at your end, and plugging it in and looking for rules, you'll have 3 answer. All right. For part of the free response questions, we're asked to figure out the equilibrium of this region. It only explicitly states, we're only looking at equilibrium, and we're already given G naught. We're going to use the equation rather than the other equation where we had both the K and Q values. Yeah, this one right here. Any Q values, so we'll use rather than this equation. All right, and discuss how you can derive K equals e to the power of negative delta over RT. Basically, chug, sure, do for this delta G in matching units of R. Since R is given in joules, just convert to joules. Units will be fine. If this to kilojoules and this get to kilojoules, I believe you'll still get the answer. And the most important thing with this is just figuring out our sig fig rules. So if I want to take an anti-log, which is just converting this value to a normal value, the sig fig rule for this is you're concerned with, so any place the ones, tens, hundreds, thousands, numbers that big, we're only concerned with the decimal places. So in reality, this be considered 1 sig fig because it's the 10th place. So our answer will be K rounded to the 1's place, or just 1 sig fig. Now, let's just say, for example, significance ended, let's just put an 8 here. I don't remember the entire here. It'll be 12.998. In significance, we're not 12 because it's not relevant for this sig fig rule. We're only concerned after the decimal point. So since we have 3 sig figs here, our would be rounded to 3 sig figs. And if you're wondering why this is the way it is, I would encourage taking analytical chemistry because I believe they cover it's a pretty higher level math concept that is, I believe it's like just like number theory that you'll have to take kind of understand why this sig fig rule the way it is. But I believe this is something that will be covered in analytical chemistry if you take it. That's all I have for questions and announcements. And I'll post the video where Corey goes over the multiple choice. If you have any questions, please reach me via email. Go look at my office for next week. It will be in library room RS1.